So today we'll be entering this one of the last exciting theme, which is lifelong machine learning. And here's an overview for today's lecture. We'll be first talking about the challenges and the need for lifelong machine learning, which is in short, you will see this acronym LML a lot throughout this lecture. And some of these challenges particularly include this constant kind of data stream that is evolving over time, and also the need for handling more than one learning task at a time. And it's also the kind of the need for retaining the knowledge and what the model has learned in the past, right? So all this need to kind of propel this field and direction of lifelong machine learning. And in today's lecture, I will be kind of covering and introducing three most commonly seen lifelong machine learning methods, including LWF, learning without forgetting, and followed by this also quite popular method, ICAR, and progressive neural networks. And lastly, we'll wrap up with other kind of interesting aspect regarding how do we grow capacity of neural networks over time, and also discover new classes. So a lot of exciting stuff for today. So before we dive into lifelong machine learning, I think it's important to kind of motivate a little bit. And this requires us to, better understand the limitations of existing approach to machine learning. And so the first limitation is that these machine learning models that we're training today are often isolated. And essentially, for every single data set, for every single task, we basically, curate a individual data set. For example, face recognition is task 1, and if you want to recognize different images of animals, you have to go ahead and create another data set and train a model for this, right? So this means the knowledge is not retained or accumulated because they are kind of not shared with each other. And also, learning is performed without considering the past knowledge of other tasks. And another limitation is you often require the data to kind of be ready prior to the training. And because your model selection or hyperparameter tuning is all based on full data set in place. And often large number of training data is needed, as we've seen this issue a lot throughout this course of the semester. And thirdly is these models are typically trained in batch mode, which means for every minute batch, subsample, randomly sample a few of those. And this inherently doesn't take into account this kind of sequential or temporal evolution of the data underneath. And of course, we assume that once you've trained this model, the underlying, testing environment is static, which we know is not true because it's already covered in this previous theme around trustworthy deep learning, especially open world machine learning. We know that the test distributions can be very different from your training distribution. And so, this motivates the importance of building lifelong machine learning. And obviously, this is a very challenging learning task in artificial intelligence. We've made some progress in this direction, but still, the community in general is facing a lot of issues, particularly, for example, data is not available priorly, and examples arrive over time. And so you have to kind of adaptively learn those new examples on the fly. And there's also the challenge of memory resource may be limited because this lifelong machine learning can only rely on this, a compact or limited collection of signals that it's observed in the past. You can't possibly, rely on accumulating or having access to, all the stuff that you've learned in the past. It's just like how we human learn, right? We grow and we learn, but we also, have limited memory that can store limited information in our brain. And the third challenge is adaptive model complexity. So it's because your task and data keeps changing, it gets very difficult to determine what is the right model capacity or complexity, right? And this complexity can be bounded by this available resources as well. And because of this, impossibility to determine this model complexity, there are a lot of other kind of hyperparameters, including learning rate or how much weight decay that you should apply. All the stuff that is standard in the batch mode of training that we use today may not be kind of generalizable to this machine learning or lifelong machine learning paradigm. And another challenge is this concept drift, which means distribution kind of changes over time. For example, you kind of expect the appearance of a person to change over time, or for example, the styles of clothing or the styles appearance of cars, right? They kind of evolve over time too. And so then this introduced this dilemma, which is stability versus plasticity. The question is when and how to adapt to these current model. And so there is kind of two extreme you can imagine. If you update too often, of course, it enables your your models to rapidly adapt to the up-to-date concepts. But you might tend to forget this old important information more easily. And versus on the other side, if you adapt too slow, you can retain this previous message and information, but then your kind of response or reactivity to your current situation is largely decreased. And so failure to deal with this dilemma lead to this problem we call catastrophic forgetting. And so I think this figure is very illustrative to this situation. It's like there's a tension between the old data versus new data, right? Strike the balance, and this is a very interesting challenge. And so this brings a line of research around lifelong machining, and the goal is to learn, retain, and use knowledge over an extended period of time. And so under this learning framework, we assume that data comes as a stream, and so it's constantly arriving and changing. It's not static. And second is we may have multiple learning tasks going on instead of just having to deal with one task, for example, classifying images of animals. And then it allows retaining or accumulate this previous knowledge and leverage that more effectively to help the future learning. And so in some sense, it's really kind of bring machine learning closer to how we human learn, right? We observe and interact with this environment, and we have to handle multiple things, and tasks at the same time. And whenever making decision, we often have to relate back to the knowledge that we obtained in the past. And so if we view this a different way, kind of this figure shows this very nicely, that on the top of this, slides here, you see the classic machine learning approach treats each task, 1, 2, 3, 4, as individual, right, objective. And so you create separate data sets, you learn different knowledge, and you perform different kind of learning task. Versus in the bottom of this figure, what it really shows that you connect all these tasks as a whole. And there's a natural kind of trajectory of how you build from the previous you've learned. For example, task 1, you start with some data there. And as you move on to the second task, you kind of expand your knowledge. And this knowledge kind of grow over time as you're exposed to more data and more tasks over time. And I think it's very intuitive to understand this whole picture here. And so this kind of touches on two learning approaches that I'm sure you're already very familiar with. The first is transfer learning, which we actually saw just in a few presentations ago, that a lot of this current machine learning paradigm moving towards pre-trained, and then you take this learned general representation and then fine-tune on your kind of target data set or learning objective. And so the idea there is to kind of use the data in the source domain to help you learn better in the target domain. And especially when these tasks are very similar, you can kind of reduce your sample complexity. So the figure on the right side basically shows the setup is to have some shared parameters, right, that is trained on your source task, and then you freeze or you fine-tune the entire network if you prefer on your target task indicated in the orange bar. And another related learning approach is multitask learn. And so the idea is to kind of jointly train on several tasks at one time. And so the typical setup is to have a shared backbone. This could be, or the convolutional layers, followed by this fully connected layer, and then branch out into different heads, one for each task. And so this requires all the tasks to be learned simultaneously, and we do require this label data to be in place for each task, and they have to be, treated equally, or you can have some weighting mechanism if you wanted to weigh one more than another. So it's really optimizing your learning, your machine learning model to kind of facilitate shared knowledge to be learned. Right, so these are, very typical, but it doesn't really address this lifelong machine learning objective. And why is that? Because if you look at transfer learning, this is sort of unidirectional from source to target, and it's not continuous because you only perform this kind of knowledge transfer in in one kind of learning round, and then your model is stagnant there on your target task, and there's really no retention of previous knowledge, because as you fine-tune or adapt onto your new task, the model can quickly forget on or perform worse on the original source task. So that's the drawback. And for multitask learning, the drawback is also very obvious because it requires you to learn all sorts of things simultaneously, so you naturally require the data to be ready. Okay, I hear a question. Let me zoom out. I'm curious to know, so Abra has this question. What is the intuition behind multitask learning? Different parts of the brain are responsible for different functions. Okay, that's a really great question. I think multitask learning is probably not covered extensively in some of the presentations. So the idea is really, if you wanted to learn, let's say, if you want to perform well on 2 tasks, right? You don't have to train 2 separate models completely, because some of these features could be shared. For example, if you want to, train a classifier to recognize all the images of cats versus another classifier to recognize images of dogs, the underlying shared feature would be, the kind of eyes or some of these kind of facial attributes, right? So the idea really is to leverage this commonality among different tasks, so you can actually get knowledge from each other. So that's kind of the idea of multitask learning. Yeah, it's not multimodal. Multimodal means if you wanted to learn, from one data modality such as language versus speech versus visual, right? So that's also standard. Abrav asks, in transfer learning, if you retrain with old and new data, can the knowledge retention problem be solved? Very good question. Yes, so we'll get to that. We'll get to that question in a bit. The problem there, and short answer, is it doesn't really simulate this lifelong machine learning, because you expect it to kind of retain your old data, which in some situation is very restrictive, right? You can't possibly expect all the training data for your previous model is saved there. And in such cases, it gets a little bit difficult to retrain everything together. But in this situation, you do get better performance than not. But the assumption on the data side is stronger. So we'll get to that. Very great question. Okay, so this is the second part of this lecture. We'll talk about 3 very common methods for lifelong learning. And so a very important technique to some of these methods that you will see later is distillation. And you probably already see this technique from the previous papers. And in fact, Yuandong's talk also covers, touch a bit on this distillation idea, right? So the goal of distillation is to transfer the knowledge that is learned from a large model into a smaller model. So the original motivation, right? So Rich Kawana and his colleagues, when they originally wrote this paper many years ago, it's really about kind of expediting the inference time for deployment time performance, and especially if you have a high-performing model trained on in form of ensemble. So ensemble is a collection of different models, which means in order to get inference finally, you have to kind of feed your data through all of these models and average their prediction. And it gets very expensive as you increase the number of models. So that's why distillation, or the idea of model compression, was proposed many years ago. And in this kind of paper by Jeff Hinton, they sort of take this the similar kind of idea, right? The goal is still to be able to train a smaller network, like a student network, that can perform as well as a teacher network. And so the core technique, as you probably have seen, or I also touched upon this work when I was describing about this Aldin method, which is temperature scaling, right? So the idea really is to advocating for the use of soft targets when you're training this student model, because these soft targets carry rich information than those hard labels. And so the idea of knowledge distillation is really to say, now you have a smaller network and you're trying to minimize this entropy loss, and you need some reference of ground truth label. And this ground truth label essentially is taking from the softmax activation from your original large model. And this goes through a temperature, which is indicated here, right? So basically you obtain this targets from your large model. And temperature essentially scales your output, here in this case, YL by a factor of T. And this essentially smoothes your output. And we can mathematically show that the effect of T through a Taylor expansion approximation. And these are, already being covered in the second lecture, actually third lecture, in the trustworthy machine learning. And so the learning objective essentially minimize the cross entropy between the student model output versus the large model output calibrated by temperature. Okay, it's the same thing. Okay, so now you have this background knowledge. Then it will help you kind of understand this following method very easily. So we'll first talk about LWF, which stands for Learning Without Forgetting. This was a paper came out in 2016. And so the goal here is to add the new prediction tasks based on adapting shared parameters without access to training data from previously learned tasks. So ABREV just asked this question, what if train on old versus new data together? This is exactly the setting that the paper is trying to explore a more realistic assumption, or a kind of closer to this lifelong learning scenario. And the high-level solution or idea of this work is to optimize for this. Of course, you have the new task and corresponding training data for this. And part of the learning objective is to try to get as high accuracy on this new learning task as possible. But simultaneously, another objective is to preserve the performance on existing tasks, which may differ from your new tasks. And so a key kind of component is how do you preserve, right, this response. And it's actually, if you think about it, you wanted to preserve the response, and the dilemma is you don't really have access to your training data of previous tasks, right? So as we will see later, this is where knowledge distillation kind of comes into the picture. And so just to keep in mind, right, you don't have access to the old data. And so this paradigm here shows the original model setup where you have some shared parameters, theta s here, So this is the whole network is divided. Let me see if I can my mouse. Okay, I don't think you can see my mouse, but I'll describe, right? So we have two kind of notations. Theta S indicates shared. So S is for shared. And theta O is for old, right? You have a bunch of old tasks that are learned on previous data from 1 to M. And each task have their own kind of heads. And this is the kind of overview for how learning without forgetting is operating. And you see this orange bar added, which is the new task that you want the model to kind of perform on with the corresponding ground truths. And so the algorithm works by the following. You start with the shared parameters and your parameters that you've learned from all these previous old tasks, one for each head. And you're provided with the training data and label for your new task, N and YN, right? N indicates new here. And so that's really the kind of the setup what you begin with. And your goal is to kind of, learn to perform well on new tasks without forgetting previous performance. And so here, the idea is really to initialize your model. You can compute the output first before optimizing, changing any parameters. You want to retain a copy of what the output for your new data looks like on this old tasks, right? So you try to take the original parameter theta S, theta O, and pass your new data, right? Here you're passing xn through this CNN, and you get this YO for this new data. And this will be very essential for this learning objective later on. And so now you have this different copies for all the new data, right? You get the, keep this output as a reference for what it produces on the previous task. Now you can start kind of tuning your model and change parameters. So this is what theta S head indicates. Kind of you start optimizing your model using this learning objective. But before you start doing any optimization, you want to make sure you retain some reference from your the previous parameters. So this learning objective, I hear a question here. Let me go through the objective, and I'll come out and address that question. Okay, so it has 3 terms here, and they're fairly straightforward. The first term is you want to kind of retain this. The first term is about retain knowledge, and to make sure that you don't lose this information from previous tasks. So essentially, it's doing a distillation here, and we're really seeing this distillation. So basically, you want to make sure that your data comes in, and whatever optimization or changes that you're doing to this entire model, you want to make sure the output on the old tasks still remains almost identical as your previous model snapshot. In the second term, L new, which is the standard kind of classification loss for your new task, right? This is about purely optimizing for this classification accuracy. And the third term, which is circled in gray here, is the weight decay, and that's the standard regularization term. All right, so I'll come out and then address the question. Is that similar to pseudo-labeling and robust self-training methods? I think it has some resemblance. So for self-training, the goal is slightly different, right? You wanted to, so in self-training, you have a collection of unlabeled data. Your goal is just to get an approximation for what the label looks like. But here, you don't really care about the label produced on the old tasks. All you care about is to make sure that after you change your model parameterization, this kind of the outputs that is derived from your new data remains more or less the same. So the label on the tasks do not matter so much. It's more about keeping that information or output consistent with respect to different model snapshots. Does that make sense? Cool. Okay, let me go back to full screen. Actually, no. To Command Option P. All right, so this is a review about how this method actually works in terms of empirical evaluation. And so this task transfer from places dataset, it's a kind of scene classification dataset to VOC. And so on the left side is the performance on the old task, and the right side is the performance on the new task. The first row is kind of their method, and the way they indicate this performance difference is by the relative, right? So minus indicates you do worse, and positive indicates it's better. So I think what's most interesting from this paper, from this table, is the last row, which is the joint training mechanism. And this is what Abrav actually asked about earlier on in this lecture, right? What if you train all together? Even though this assumption is not realistic, right? Because it requires access to your old data. But you can view this as sort of your upper bound performance, under this, this unrestricted assumption, how well you can. And of course, in this case, your old data performance would have some bump compared to LWF, just because you have more, access data there. But interestingly, right, the performance on your new data is very kind of comparable. So this shows the method is overall achieving a pretty good trade-off, right, in terms of doing well on new tasks and also simultaneously not terribly forgetting what it has learned before. So this is something hopefully address the question raised early in this lecture. All right, so that was the first method, and now let's move on to kind of a follow-up method called ICAR. And it's a very kind of tricky name for me to kind of pronounce. And so the goal here is to add new classes based on adaptive shared parameters with restricted access. So here I built this assumption, which means it has a less strict assumption to previous method. And what this means is, you possibly can't retain all the data from previous training process. It might be okay, right, if you have a limited kind of memory bank somewhere to store some representative data, which in this paper they call exemplar set. So the idea is really to restrict your data to a portion, maybe a small portion that you learned from previous task. And here is the solution sketch. I'll give you the first kind of overview, and then we dive into the specific algorithm one step by another. And so the idea, like I said, is to retain a small subset of training samples called exemplar set from the previous classes learned. And in each training round, the classification loss is the combination of very similar. The classification laws for the new examples, and simultaneously you have this distillation laws for the old examples. And so this is in some sense very similar to what LWF is doing. And because it's a follow-up work, I think it has some inherent some spirit and kind of methodology similarity there. And a third key component is to kind of keep this like a memory bank or the size of your exemplar set consistent, because you want to kind of grow your exemplar set infinitely as you accumulate more classes over time. And so as you have more classes come in, part of what this algorithm requires is to remove some of these examples from your classes, so you can maintain a relatively fixed memory consumption here. And these are the kind of assumptions that this method operates on. Right? So I think it's very important to be clear and articulate these settings, because as you read lifelong machine learning papers, you would realize, right, that the settings can be differ from one another. Okay, so this is the sketch of this algorithm, and we start with input, which is XS to XT. These are the new training examples that is used for incremental learning. And so you can think of this as a total number of T different classes, and from 1 to S minus 1 are the classes that has been learned in the past. And starting with S, it's a start point. To T are the new classes to be learned. So that's it's very important to differentiate these two, because you will see these two notations a lot in this paper. And K is your memory size, which is again constant. And theta is your current model parameters. And something unique to this algorithm is the requirement to the exemplars P. And this subscript ranges from 1 to S minus 1, right? These are the old classes that the model previously trained on. Okay, so this is a kind of a module for update representation, which you can take this as a grain of thought. We will dive into this function in the next slides, but essentially at a high level, provided with input, you update the parameters based on your new training example classes, and then what you do is to reduce the number of exemplars per class, because you want to retain a constant memory bank. So you have to kind of adjust this accordingly. And then the rest functions, what it does is really to reduce the exemplar set for your old classes, right? In order to keep only M examples in one class, and then you construct a exemplar set for your new classes. Right? So and then finally you form this new exemplar sets for all classes 1 to T. And I think the right side of the figure is very clear about what it's trying to achieve, right? You have this fixed memory bank, and you kind of select and merge and keep everything constant. Okay, so now we will demystify this missing step, which is update representation, which is where the learning comes to happen. Okay, so here we have, again, the training images for your new classes S all the way to T, and exemplar set, which you already saw, and the current model parameters. And so your overall training data is composed two parts. The one highlighted in green is the new data, and the one highlighted in purple is the old data. And so before you update any parameters, the idea is to kind of pre-update before update parameters. You want to get a kind of a output for your previous class, which is 1 all the way to s-1, to retain a copy of the outputs, because this will be used in this distillation loss, which again, you're already very familiar with this. And so here the goal for the first part of the loss is to perform classification, right? This is the standard classification loss, logistic loss. And the bottom part is the knowledge distillation loss, because you want to make sure on your exemplar set, whatever the model is producing, right, on the current parameter, is mimicking the previous snapshot, right? This is, I think, a lot easier to understand because now you know how LWF works. So here's how the method performs. We see on this, for example, on the left side is the accuracy of the ImageNet top 5 accuracy. Right? So the x-axis varies the number of classes, and you should look at dark blue, which is at the top, right? That's where this method stands. And then LWF, which we saw earlier, is this green curve. And as you can see, this I-curve performs a lot better compared to LWF. But also keep in mind, I think this is perhaps not exact apple-to-apple comparison, because this method does require storing some exemplar sets, right? So this gives additional advantage to this algorithm. And in fact, a lot of this benefits on the performance side does come from having this access to previous data. All right, so lastly, I will cover another interesting work really quick. This one I won't dive into too much detail. It's a paper published by this group at DeepMind on progressive neural networks. And so the idea is to learn a series of in sequence using knowledge from the previous task to improve convergence speed. So what we have seen so far is that the network's backbone remains more or less the same, right? You just stack up different task head on top. But the previous method may run into issue because you may run out of capacity as you add more and more learning tasks. Because remember, as your number of tasks grows, you should be able to support the learning effectively by allocating more capacity in terms of model parameters. And so this paper can explore this idea by dynamically expanding your networks in this lateral direction. So what this doing is really first learn a task, right? Look at this figure, the leftmost side. You first learn task 1, and as you progress to your new task, you add some lower connections to the previously learned features. And so your kind of heavily relies on what it has learned before. And so your internal hidden representation now has to combine not just the connection to your, okay, so this is okay, so let's look at this H2, right, this middle block here. And so in order to get this hidden representation, you have to, rely on not just your current, this network, but you also have to take into account this left side of the model. So it really gets more complicated over time because, you have to, rely on more and more things from the previous columns. And of course, a downside of this method is your method, this capacity kind of grows linearly as your number of tasks. And during test time, you also have to know your task label in advance in order to kind of route this method into the right column. So this is really the gist of this method. I'm personally, I think this paper kind of explores something, very, very raw and interesting, but it does have some, significant limitation, which actually they have some follow-up paper if you're interested in reading. Okay, so here is a summary of the 3 methods that we've covered, and this paper, this table kind of listed here some of these assumptions, right? It's made for this method. So as you can see, ICAL in the first method requires old data to be retained, whereas the other 2 methods is not. And in terms of learning methods, the first 2 are more or less resembling each other. Both of them rely on this key technique of knowledge distillation. You can think of this as a regularization to prevent this catastrophic forgetting issue. All right, so another aspect I want to touch upon towards the third part of the lecture is how do we increase model capacity and discover new classes. So, this is already kind of very similar to what we just talked about. The motivation here is really to kind of, because we have to accommodate new knowledge over time, and those new classes or new data may saturate your network capacity over time. And the optimal model complexity would change as your training data changes over time. So initially, you might have a very small model because you have a small amount of data. So that is fine. But later, when you have a much larger data, you have to grow, like this figure shows, right? Maybe double your model capacity to accommodate for this. And so this progressive networks are already doing some of these, like we saw earlier. And the key missing bit, right, is, as you grow the capacity, you don't necessarily want to retrain this whole network from scratch. And so the idea in this net-to-net paper, which was an iClear paper in 2016, is kind of proposing a method that allows you to train a bigger student network in an efficient way without having to retrain everything from scratch, right? So this is really the opposite motivation of previous teacher-student setting, where you want to compress this student network because you want to optimize for deployment efficiency. Here, your goal is slightly different, right? It depends on your scenario, right? The scenario here is we want to obtain a bigger model without, sacrificing on this performance that is already learned on the smaller network. And so I think this figure is very illustrative. On the left side is the traditional overflow, where you have a smaller data set, smaller network. You go through this training, and every time you change your model capacity, you just rebuild the model, basically train from scratch again. And so net-to-net workflow allows you to kind of reuse the previous model, which is a smaller network, right? This kind of small little yellow block, and reuse this to expand, widen your network in a way that doesn't sacrifice the performance. And so here it gets into some of the details, but their method essentially allows you to initialize the network with bigger capacity, but guarantee to be an improvement, as long as each local step is an improvement. So what does this mean? Okay, let me explain this in a very simple way. And so here is a very simple example to illustrate how you can construct a bigger network on the right side from a smaller network, which preserves the same classification performance or accuracy. So the idea is really simple. So let's say originally you have, two inputs, dimensions, x1 and 2, and each of those is connected to hidden representation or hidden neurons. And then you have this final output y. And say now we want to expand your hidden intermediate layer by another neuron. And so what it does is to copy this weight connection here. You have this original weight connection with magnitude C and D to this H2. Now you just copy exactly the same weight to H3, right? And then what you do is to reduce this output or outgoing weight from H2 and H3 by half. And so this overall ensures that your final output, effectively, it's just copy H2, decompose the original activation of H2 into kind of, two kind of twin neurons, and reduce their weight by half, so the output doesn't change. So this is a kind of the underlying simplified idea of this net-to-net, which allows you to retain this performance as with respect to the student network. So that's growing capacity. And there are a lot of other interesting kind of follow-up works that unfortunately due to time limit we wouldn't be able to cover. But I think this is one kind of interesting and very easy to understand approach that you should know. And lastly, I just want to briefly touch on this discovering new classes. And the motivation, I think it's very straightforward and illustrated in this figure below. For example, if you want to learn this concept of a car, their appearance, right? These models change over time. And so it requires you to recognize these new classes. And unfortunately, when we're making this closed word assumption that the categories are predetermined during training time is no longer holds in open word, right? And we have to kind of identify and detect those changes or concept drifts. And this really is related to the problem of out-of-domain distribution and out-of-distribution detection that I already talked about in one of the previous lectures. So you can think of out-of-distribution being this component that allows you to identify the unknowns, right? What the current cannot generalize to. as a way to kind of discovering these new classes. And so ultimately, in order to build this lifelong machine learning system, all these pieces need to kind of come together, right? You need algorithms that allows you to identify new classes, and you also need mechanism and algorithms to adapt to those new classes without forgetting what it previously learned, right? So ultimately, it relies on all these components to kind of make the system work, which is extremely challenging, and it takes years of fundamental research to get there. And currently, we are working actively in this space, which I personally think is very exciting and important. All right, so to recap, we talked about a lot of stuff today. And to refresh your memory, the lecture started with the need and challenges for lifelong machine learning, and I hope by now you kind of have a better kind of understanding about the challenges that is faced, which include constant data stream and learning multiple tasks, not necessarily simultaneously, but it could be in some sequential manner. And you wanted to be able to retain knowledge without catastrophic forgetting, which is another important challenge to solve. And we have looked at 3 methods, which are very representative and classic. The first one is learning without forgetting. This one makes this less restrictive assumption that you only have the current data for your new classes available. And the key idea is to use knowledge distillation to regularize your model output on the previous task, so that it doesn't change too much, even though you're adapting to a new task simultaneously. And the second method I call is very similar, except for the data assumption is less restrictive. It allows you to have access to some portion of the data from previous classes, which is called exemplar set. And the learning loss, again, is very similar, comprised of classification loss on your new task, plus a knowledge distillation loss on the previous task. And lastly, I talked briefly about progressive neural networks, and the links of all these papers are all on the website if you're interested in having kind of a deep dive reading. And we will see some of the more recent, more up-to-date paper that builds on top of these papers in the next presentation, which I'm really kind of excited. It's a paper by Kimi, and I've been following, and a lot of his work are very relevant to my research personally. So I'm pretty excited about that. And in the last component, we talked about this growing capacity using this net-to-net technique. And progressive neural networks is also related to this, this objective, but does have some, flaws in terms of linear expansion of capacity over time, which is really kind of gets out of hands if you have too many tasks to kind of learn sequentially. And discovering of new classes is also an interesting topic, and in some sense it's like a precursor problem to be solved in order to do any of these fancy adaptation. So what I found currently largely missing in the literature in this LML papers is sort of taking the setup for granted, right? You can always artificially construct these learning tasks by assuming these new classes are already reviewed to you. But in reality, right, you do have to go through or design algorithm to identify them in some way. And this is, in some sense, the key kind of research bottleneck that we are trying to kind of solve in order to kind of truly enable this end-to-end lifelong machine learning paradigm. So I think, overall, it's a very exciting space to be in. And with that, I would like to open up to questions. And let me